What if I told you that a single photograph from this new telescope would require 378 4K TVs to display at full resolution? The Vera Rubin Observatory has just released its first images, and they're unlike anything we've ever seen before. This isn't just another telescope. It's housing the largest digital camera ever built, weighing as much as a small car and capturing 3.2 gigapixels in a single shot. But here's what's really mind-blowing. In just one night, this beast can gather 20 terabytes of data, and over the next 10 years, it will revolutionize our understanding of dark matter, dark energy, and the entire universe. The world of astronomy has just entered a brand new chapter. For years, our attention has been fixed on space telescopes like Hubble and the James Webb, which orbit high above Earth's atmosphere and return stunning portraits of distant galaxies, nebulae, and star systems. These telescopes have shaped the way we imagine the cosmos. But now, here on Earth, another instrument has stepped into the spotlight, and it is already making waves with its first-ever images. This is the Vera Rubin Observatory, perched high in the Chilean Andes. In June of 2025, the Rubin Observatory released its first official images, marking the beginning of what many astronomers believe will be the most ambitious sky survey in human history. It is not just another telescope. This facility represents a leap forward in how we observe the universe. From its home on Cerro Pachón, a mountain in Chile's Atacama Desert, it has begun showing us the universe in ways we've never seen before. At the heart of the observatory lies a technological marvel, the largest digital camera ever built. Imagine a camera the size of a small car, weighing nearly 3 tons, suspended at the end of one of the world's most powerful telescopes. This is the Eye of Rubin. With a resolution of 3.2 billion pixels, it can capture an image so detailed that displaying just one photograph would require an entire wall of 385 ultra-high-definition 4K televisions. That is almost incomprehensible. For context, the camera on your phone probably has somewhere between 12 and 50 megapixels. This camera has 3.2 billion. Each time it clicks the shutter, the observatory produces a colossal amount of information. But it is not only the size of the images that is extraordinary, it is what those images allow us to do. Astronomers can now see vast portions of the night sky in breathtaking detail, spotting not just individual stars and galaxies, but millions upon millions of them in a single frame. These first images represent the tiniest glimpse of what Rubin will eventually reveal, a universe alive with activity, structure, and mystery. This achievement did not happen overnight. Astronomers, engineers, and data scientists have been working toward this moment for decades, dreaming of a facility that could capture the universe not just as a series of snapshots, but as an unfolding story. And now, that dream is real. The Rubin Observatory stands ready to map the sky like never before, building not only a detailed record of the universe as it looks today, but also a dynamic, time-lapse portrait that will unfold over the next 10 years. In this opening chapter, we are witnessing history. The very first light from Rubin is proof that the project works. And more than that, it is proof that humanity's ability to observe the cosmos is entering an entirely new era. The power of this telescope and its gigantic camera will soon allow us to catalog billions of objects, track fleeting cosmic events in real time, and answer some of the most profound questions about our universe. This is just the beginning. If you thought the size of Rubin's camera was impressive, wait until you hear about the data it produces. Every single night, the observatory gathers around 20 terabytes of information. To put that into perspective, 20 terabytes is the equivalent of streaming nearly 4,000 high-definition movies, all recorded in one evening of observing the skies. And Rubin will do this night after night, year after year. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. Over the course of a decade, The project is expected to accumulate around 500 petabytes of data. That number might not mean much at first glance, so let's slow down and put it into context. 1 petabyte is 1,000 terabytes. That's 1,000,000 gigabytes. 500 petabytes is 500,000 terabytes of pure astronomical information. If you tried to store that on regular laptops, it would take hundreds of thousands of them stacked together. If you wanted to download it all at home, even with the fastest internet speeds available today, it would take you many lifetimes. It is not just a mountain of data, it is an entire continent of information. Handling that flood of information requires infrastructure on a scale almost as impressive as the telescope itself. Rubin sits in Chile, in one of the most remote desert regions in the world, but its discoveries are meant to be shared with scientists across the globe. To make that possible, engineers built a dedicated 100 gigabit per second internet connection stretching from the observatory in the Atacama Desert all the way to Miami, Florida. From there, the data taps into existing fiber optic backbones that distribute it to supercomputing facilities in the United States. That means the images Rubin captures each night travel thousands of kilometers almost instantly. Think about that for a moment. Photons of light that left a distant galaxy millions or even billions of years ago finally arrive at Rubin's mirrors. They are captured by its massive camera, converted into data, and then, within seconds, those signals are racing under the ocean through high-speed fiber optic cables, landing in Miami, and then scattering out across the scientific world. It is a breathtaking journey. Light that traveled for eons, now transformed into information and made available to human minds. But moving the data is only part of the challenge. Storing and analyzing it is just as daunting. Each night's 20 terabytes must be cataloged, processed, and added to an ever-growing archive. By the end of the project, researchers will be dealing with one of the largest scientific data sets ever created. To cope with this, Rubin is supported by some of the most powerful supercomputers in existence, capable of sifting through trillions of measurements to identify what matters: a faint asteroid moving against the background stars, a supernova exploding in a distant galaxy, or a subtle shift in the brightness of a star that might suggest the presence of an exoplanet. In this sense, Rubin is not just a telescope, it is a data machine. Astronomy is no longer about staring through an eyepiece at the night sky. It is about capturing torrents of digital information and using advanced algorithms, machine learning, and human insight to make sense of it. The observatory represents the cutting edge of what some call big data astronomy, where discovery is driven not just by optics, but by computation. This constant stream of information is what will allow Rubin to do something no other telescope has ever done: to build a dynamic, living movie of the universe, one that captures not just where objects are, but how they change over time. Without this robust data pipeline, the project would be impossible. But thanks to modern networking, computing power, and human ingenuity, the Rubin Observatory is prepared to handle the flood. And this is only the foundation. With the data pipeline secure, the observatory can now turn to the real work, what it's all for. And to understand that, we need to look at the person whose name the observatory carries, and the extraordinary legacy she left behind. Before we dive further into what this observatory can do, it's important to pause and reflect on the name it carries. The Vera Rubin Observatory is not just a machine for science. It's also a tribute to one of the most influential astronomers of the 20th century. Dr. Vera Rubin. In the 1960s, Rubin made a discovery that changed astronomy forever. At the time, scientists assumed that galaxies behaved in a fairly straightforward way. Stars near the center of a galaxy orbited faster, while those farther out moved more slowly, much like planets in our own solar system orbit the sun. That was the prediction. But Rubin's careful measurements told a very different story. She found that stars on the edges of galaxies were orbiting just as quickly as those near the center. According to Newtonian physics, that shouldn't have been possible. The galaxies should have flown apart. The only explanation was that something invisible was holding them together, an unseen mass that outweighed the stars, gas, and dust we could detect. This was the first solid evidence for what we now call dark matter, the mysterious substance that makes up most of the matter in the universe. It was a groundbreaking revelation, one that continues to shape the biggest questions in cosmology to this day. What makes Rubin's achievement even more remarkable is the context in which it happened. In the 1960s and 70s, women were almost absent from professional astronomy. The field was dominated by men, and opportunities for women were severely limited. Vera Rubin pursued her research anyway, pushing against the current of her time. She not only produced revolutionary science, but also managed to balance her demanding career with raising 4 children. She was, in every sense, a pioneer. By naming this observatory after her, the astronomical community is doing more than just honoring her scientific legacy. They are acknowledging her perseverance, her vision, and her role as a trailblazer for future generations of scientists, especially women who aspire to careers in astronomy and physics. It is a recognition that great science is not only about equations and instruments, but also about the courage to ask questions that no one else is asking, even when the world doubts you. And just as Vera Rubin revealed the hidden scaffolding of galaxies, the observatory that bears her name will seek to uncover the hidden dynamics of the universe itself. It will probe dark matter and dark energy on scales never attempted before, potentially providing the clues we need to unravel the deepest mysteries of the cosmos. So when we speak of the Vera Rubin Observatory, we're not only talking about mirrors, cameras, and data pipelines. We're talking about a living legacy, a continuation of one woman's quest to reveal the unseen, to make the invisible visible, and to remind us that the universe always has more secrets waiting to be discovered. With that spirit in mind, let's take a closer look at how the observatory is designed, and why its location and unique telescope architecture make it such a powerful tool for exploring the night sky. To unlock the universe's deepest secrets, location is everything. The Vera Rubin Observatory sits atop Cerro Pachón, a mountain in Chile's Atacama Desert. This region is world-famous among astronomers. It's one of the driest places on Earth, with skies so clear that rain may not fall for years at a time. The thin, dry air means far less atmospheric distortion, and the high elevation places the telescope above much of the atmosphere's turbulence. Combine that with minimal light pollution, and you have some of the most pristine observing conditions on the planet. It's no accident that Chile has become the global capital of ground-based astronomy. Cerro Pachón is already home to several major observatories, and Rubin joins them as a crown jewel, designed specifically for wide-field surveys of the night sky. At the heart of Rubin is the Simony Survey Telescope, which ranks as the 7th largest optical telescope in the world. Its design, however, sets it apart from almost everything built before. Most large telescopes rely on 2 mirrors, a primary to gather light and a secondary to focus it. Rubin, on the other hand, uses a 3-mirror system, something extraordinarily rare in astronomy. The telescope's primary mirror is a massive 8.4 meters across, carved and polished with extraordinary precision. Then there's the 3.5-meter secondary mirror, suspended high above the primary. But what truly makes Rubin unique is the inclusion of a 5-meter tertiary mirror. This trio of optics works together to eliminate distortions that plague traditional telescope design. The result is a much sharper, cleaner image across a much wider field of view. Think of it this way. While most giant telescopes act like narrow spotlights, focusing deeply on one small region of the sky, Rubin acts more like a wide-angle lens, capturing enormous swaths of the heavens at once. With its 3-mirror design, the telescope can observe a patch of sky about the size of 40 full moons in a single exposure. That is unprecedented for an instrument of this scale. The engineering required to make this possible is staggering. The mirrors themselves had to be cast, cooled, and polished with a precision measured in nanometers. They are supported by advanced control systems that adjust their positions in real time to counteract tiny shifts caused by temperature or gravity. Even the telescope's dome and supporting structures were built with airflow in mind, designed to minimize turbulence that could blur images. Why go to all this effort? Because Rubin's mission demands it. This is not a telescope meant to take isolated snapshots. It is built to map the entire sky, again and again, night after night, with unparalleled clarity. Its wide field of view allows it to capture billions of stars, galaxies, and transient events in a single survey. And that wide field only works because of its innovative three-mirror architecture. The Rubin Observatory is, in essence, a marriage of location and design. The Atacama provides the perfect skies. The Simone telescope provides the perfect optics. Together, they form one of the most powerful survey instruments ever constructed, one capable of rewriting our cosmic map not once, but thousands of times over the next decade. And what will all this effort reveal? The answer lies in the ambitious mission of Rubin, to create the most detailed time-lapse movie of the universe ever attempted. If the mirrors of the Rubin Observatory are its eyes, then the LSST camera is its brain, the component that captures the universe in exquisite detail. And this is no ordinary camera. It was designed specifically for Rubin's flagship mission, the Legacy Survey of Space and Time, a 10-year effort to record the changing sky like never before. The scale of this camera is hard to grasp. It measures about 3 meters long and 1.5 meters wide, roughly the size of a small car, and it weighs nearly 3 tons. Engineers had to design custom support systems just to move and install it, because no standard camera mount on Earth could handle something this massive. At its heart are 189 custom-built CCD sensors, charge-coupled devices, each engineered for extreme sensitivity to faint light. Together, they form a mosaic of 3.2 billion pixels, making this the largest digital camera ever constructed for astronomy. For comparison, if you wanted to view a single full-resolution image taken by the LSST camera, you'd need nearly 400 4K televisions lined up side by side. That's the sheer amount of information this instrument captures with every shot. But what makes it truly special is its field of view. The LSST camera can image 10 square degrees of the sky at once, about the area covered by 45 full moons. This wide-angle capability is what allows Rubin to scan enormous regions of the heavens in a single glance. Instead of spending weeks staring at one patch of space, Rubin can cover the entire visible sky every few nights. Over 10 years, it will build up a dynamic, evolving map of billions of celestial objects. To make this possible, the camera is equipped with a set of interchangeable filters, each designed to capture a different slice of the spectrum. These filters range from the ultraviolet, through visible light, and into the near-infrared. That means Rubin doesn't just take pretty pictures. It collects physical data about the temperature, composition, and distance of the objects it observes. Each filter adds another layer of scientific depth, turning photographs into rich data sets. The engineering that went into this camera is almost as fascinating as the science. The sensors must be cooled to extremely low temperatures to eliminate electronic noise. The shutter mechanism, the device that opens and closes to take an exposure, is one of the largest ever built, yet it must operate with incredible precision, opening and closing in just milliseconds. Even the lenses that guide light onto the detectors are extraordinary. One of them, over 1.5 meters in diameter, is the largest optical lens ever made. All of this precision and scale comes together for one purpose: to create the Legacy Survey of Space and Time, a 10-year movie of the cosmos. Every 3 nights, Rubin will scan the entire southern sky, capturing anything that changes: an exploding star, a wandering asteroid, or the faint flicker of a galaxy billions of light-years away. By the end of the survey, scientists will have the most complete time-lapse of the universe ever assembled. This camera is not just a tool, it is a cosmic storyteller, documenting the drama of the night sky in a way that no human eye ever could. And the story it reveals is one of movement, transformation, and mystery. Next, Let's explore what this ambitious survey, the LSST itself, will actually achieve, and why astronomers believe it will revolutionize our understanding of the universe. What truly sets the Rubin Observatory apart isn't just its mirrors or its record-breaking camera. It's the sheer scale and speed of its survey. Once fully operational, Rubin will scan the entire southern sky, about half the celestial sphere, every 3 nights. That means, in less than a week, astronomers will have a fresh, complete map of billions of stars, galaxies, nebulae, and moving objects. And Rubin won't just do this once. It will repeat the process again and again, building a rolling archive of the sky's changes over time. Over the course of a decade, that adds up to thousands of passes across the heavens, creating something no telescope has ever achieved: a time-lapse movie of the universe itself. Instead of isolated snapshots, scientists will have a dynamic record showing how the cosmos evolves, how galaxies collide, how stars are born and die, and how objects shift across the vastness of space. To understand just how powerful this is, it helps to look back at one of the most important surveys in astronomy's history, the Sloan Digital Sky Survey, or SDSS. Beginning in the year 2000, Sloan slowly pieced together an unprecedented map of the universe. Over 20 years of observations, it managed to chart around 35% of the sky. This was groundbreaking at the time, giving astronomers their first real cosmic map on a galactic scale. But compare that to Rubin. What Sloan required 2 decades to accomplish, Rubin can replicate in just 3 days. That's not an incremental improvement. It's a leap of several orders of magnitude. The pace at which Rubin will collect data means that what was once considered monumental progress is now the baseline of a nightly routine. Think about the implications of this. A supernova that might have gone unnoticed for centuries could now be captured the very night it explodes. A small, dim asteroid drifting near Earth won't remain hidden. Rubin will detect its faint movement against the starry background almost immediately. Even subtle shifts in the brightness of distant stars, which could hint at the presence of new exoplanets, will be recorded in the survey's endless stream of observations. This relentless coverage transforms the sky into something alive, something that can be watched as it changes. It's a new way of doing astronomy, one that shifts the field from static charts to a living, breathing narrative of the universe. For researchers, it means they no longer have to wait years or decades for enough data to appear. For the public, it means the discoveries will come fast and often, with new revelations appearing almost daily. Rubin doesn't just outpace its predecessors, it redefines what a sky survey can be. And the payoff of this revolution will ripple through nearly every branch of astronomy, from the study of dark energy to the hunt for hazardous asteroids. Next, we'll dive into one of Rubin's most exciting promises: how this observatory could fundamentally change our understanding of dark matter and dark energy, the mysterious forces that make up most of the universe. So far, we've seen how the Rubin Observatory is an engineering marvel. Its massive mirrors, record-breaking camera, and sweeping survey capabilities. But what is all of this power actually for? What questions does Rubin hope to answer? The truth is, the observatory has 4 central scientific missions, each one capable of reshaping our understanding of the cosmos. The first mission is to study dark matter and dark energy. Vera Rubin herself discovered the strongest evidence for dark matter, and now the observatory that carries her name will push that frontier forward. By mapping billions of galaxies across time and space, Rubin will measure how their distribution and motion are influenced by gravity. The patterns it uncovers will reveal how invisible matter is woven through the universe like a hidden skeleton. At the same time, it will track how galaxies move apart, providing new insights into dark energy, the mysterious force driving the accelerating expansion of the universe. Together, these observations could give us our clearest clues yet about the invisible forces that make up 95% of the cosmos. The second mission is to catalog solar system objects. From nearby asteroids to icy comets at the edge of our system, Rubin will detect and track countless small bodies. Its sensitivity is so great that it could spot a faint asteroid only 100 meters wide from tens of millions of kilometers away. That means Rubin will play a critical role in planetary defense, helping scientists identify objects that could one day pose a threat to Earth. And it won't stop there. Rubin may also detect new dwarf planets, Kuiper belt objects, and perhaps even more interstellar visitors like the famous Oumuamua, giving us a better sense of how our solar system fits into the larger galactic neighborhood. The third mission is to monitor transient cosmic events. Most telescopes take static images, but Rubin will be watching for things that change. That includes supernova explosion, when dying stars briefly outshine entire galaxies. It includes gamma-ray bursts, some of the most energetic events in the universe, often linked to the collapse of massive stars or the merging of neutron stars. Rubin will also track variable stars, flaring quasars, and countless other cosmic fireworks. Because the survey covers the whole sky so frequently, astronomers will no longer need luck to catch these events. They'll have a front row seat every time something dramatic happens in the heavens. The fourth mission is to map the structure of the Milky Way. For centuries, humanity has looked up at the night sky and wondered about our home galaxy. Rubin will provide a view of the Milky Way with a level of detail that was once unimaginable. It will chart the precise positions, motions, and brightness of billions of stars, revealing how our galaxy formed and how it continues to evolve. By studying streams of stars pulled from ancient collisions with smaller galaxies, Rubin will reconstruct the Milky Way's history, showing us not just where we are, but how we came to be. These four pillars, dark matter and dark energy, solar system science, cosmic transients, and galactic structure, are not separate goals. They're interconnected parts of a larger story. Together, they represent Rubin's promise to transform the way we see the universe, from the nearest asteroid to the farthest galaxy, from fleeting flashes of light to the slow arc of cosmic history. In many ways, the Vera Rubin Observatory is less a telescope and more a time machine, a tool that lets us explore both the past and the future of the universe. After years of anticipation, the Vera Rubin Observatory has finally shared its first official images, and the results are nothing short of breathtaking. These early releases offer a glimpse into the scale, detail, and ambition of what Rubin will achieve over the next decade. One of the standout images is called the Cosmic Treasure Chest. This incredible mosaic focuses on a portion of the Virgo Cluster, a massive collection of galaxies located approximately 55 million light-years away. But the mosaic is far more than just a pretty picture. It was constructed from 1,185 individual exposures, taken over 7 nights, each capturing faint details that might otherwise go unnoticed. When combined, these exposures reveal an astonishing 10 million galaxies in a single view. And yet, this represents just 0.05% of the 20 billion galaxies Rubin is expected to observe over the course of its 10-year survey. It's a humbling reminder of both the immensity of the cosmos and the unprecedented scope of this project. Zooming in on the mosaic, the level of detail is staggering. Spiral galaxies twist gracefully. Threads of intergalactic material stretch between merging systems, and groups of both nearby and distant galaxies populate the scene. Foreground stars from our own Milky Way twinkle like tiny beacons against this distant cosmic backdrop. Across the image, the variety of structures and formations is so vast that even a single frame feels like a universe unto itself. Another striking early release is the Lagoon Nebula mosaic, created from 678 exposures over just 7 hours. This mosaic showcases several celestial landmarks, including the Lagoon Nebula, Messier 8, the Trifid Nebula, Messier 20, the Open Star Cluster, Messier 21, and the tightly packed globular cluster, NGC 6544, home to tens of thousands of stars. What's immediately apparent when comparing Rubin's view to Hubble's images is the sheer scale of the field of view. While Hubble specializes in zoomed-in, ultra-detailed snapshots of individual objects, Often spanning only a few light-years, Rubin captures the vast surrounding context. The Lagoon Nebula, for example, spans roughly 55 light-years across and 20 light-years tall. In Hubble's optical images, it appears as a close-up, while in Rubin's wide-angle mosaic, it is a small part of a much larger cosmic neighborhood, surrounded by clusters and nebulae that are visible simultaneously. Another fascinating aspect of these mosaics is how the observatory combines multiple exposures taken with different filters to capture ultraviolet, visible, and near-infrared light. These wavelengths reveal details the human eye could never see on its own, allowing astronomers to map temperature, composition, and subtle structures within stars and nebulae. Infrared light, often associated with cooler objects, might appear red, while ultraviolet, linked to hotter regions, can be displayed as blue, creating both a scientifically rich and visually stunning representation of the cosmos. The Cosmic Treasure Chest and Lagoon Nebula mosaic are only the beginning. They demonstrate Rubin's ability to capture enormous regions of the sky in unprecedented clarity, while simultaneously revealing the countless smaller details that make the universe so complex and beautiful. In essence, these early images offer a preview of what will become the largest, most detailed and most dynamic survey of the night sky ever attempted. As remarkable as these first images are, they are just a taste of what's to come. Over the next decade, Rubin will continue to map billions of galaxies, track millions of asteroids, monitor fleeting cosmic events, and build a living, evolving portrait of the universe itself. Even before the Vera Rubin Observatory officially begins its full survey, the first test observations have already produced remarkable results, hinting at the transformative impact this telescope will have on astronomy. In just 10 hours of operation, Rubin demonstrated the power of its unprecedented field of view, high resolution, and rapid scanning capabilities. One of the most exciting early results was the discovery of 2,104 previously unknown asteroids. Among these, 7 were near-Earth objects, small bodies that pass relatively close to our planet. Thankfully, none of them pose any threat to Earth. Still, this early haul demonstrates Rubin's extraordinary ability to detect faint, moving objects that may have gone unnoticed by other surveys. Over the next 2 years alone, Rubin is expected to discover millions of new asteroids, vastly expanding our knowledge of the solar system and improving our ability to track potentially hazardous objects. Rubin is not just cataloging solar system objects, it's also helping astronomers spot interstellar visitors, like the mysterious Oumuamua and 2I Borisov. These rare visitors pass through our inner solar system perhaps once a year, but until recently, we lacked the capability to detect them reliably. With Rubin scanning the sky every 3 nights, it becomes far more likely that future interstellar travelers will be spotted as soon as they arrive, providing crucial data on objects originating outside our solar system. Another early discovery from the test phase was the identification of 46 RR Lyrae stars, a class of pulsating stars that serve as cosmic distance markers. By measuring their pulsation periods, astronomers can calculate how far away these stars are, providing a 3-dimensional map of the outer reaches of the Milky Way. This is just the beginning. Over the course of the survey, Rubin is expected to find up to 100,000 RR Lyrae stars, potentially mapping stars that lie more than 1 million light-years from Earth. This will offer unprecedented insight into the structure and history of our galaxy's halo, revealing streams of ancient stars left over from past mergers with smaller galaxies. Even in its test phase, Rubin is already demonstrating its ability to combine solar system science with galactic and extragalactic studies. It can track tiny asteroids moving against the backdrop of distant stars, identify pulsating stars that trace the structure of our galaxy, and simultaneously reveal the intricate architecture of millions of galaxies in the background. This integration of multiple scales of observation, from near-Earth objects to intergalactic structures, is exactly what makes Rubin revolutionary. These early discoveries are just a glimpse of the scientific potential Rubin will unlock. Over the next decade, astronomers will rely on its data to monitor transient events, map dark matter, study the Milky Way in exquisite detail, and perhaps make discoveries that no one can yet imagine. Even in the test phase, it is clear that Rubin is not just another telescope. It is a game-changer for observational astronomy, capable of transforming our understanding of the cosmos from the ground up. Looking ahead, the Vera Rubin Observatory promises to be one of the most transformative instruments in the history of astronomy. Its early test phase results are only a glimpse of what's to come. Over the next decade, Rubin is expected to identify millions of new asteroids, including previously hidden near-Earth objects, improving our planetary defense capabilities while vastly expanding our knowledge of the solar system. But Rubin's impact doesn't stop with asteroids. Because it scans the southern sky every 3 nights, the observatory can catch rare cosmic events in real time. Supernovae, gamma-ray bursts, and other transient phenomena will no longer be fleeting mysteries. Astronomers will have a continuous record, allowing them to study these events from the earliest moments onward. This real-time monitoring opens doors to discoveries that are impossible with slower, narrower surveys. A key part of Rubin's power lies in its massive field of view, combined with unprecedented image detail. Its 3.2 billion pixel camera can capture about 4,000 times the area of sky in a single shot that Hubble can. That means Rubin is perfect for big sky surveys, capturing the broad structure of the cosmos while simultaneously revealing tiny details within galaxies, star clusters, and nebulae. It's like seeing both the forest and every individual leaf at the same time. The observatory will generate an enormous data legacy, approximately 500 petabytes of images and measurements over 10 years. That's 500,000 terabytes of data, containing billions of stars, galaxies, and other celestial objects. Researchers around the world will use this treasure trove to test theories, discover new phenomena, and push the boundaries of our understanding. Machine learning, artificial intelligence, and other modern tools will be essential to sift through this volume of information, making Rubin not just a telescope, but a platform for data-driven discovery. By combining wide-angle, high-detail imaging with long-term, repeated monitoring, Rubin will allow astronomers to see the dynamic universe in action. Galaxies will collide, stars will explode, asteroids will move across the sky, and even subtle changes in stellar brightness will be tracked and catalogued. The universe will no longer appear static. Instead, it will emerge as a constantly evolving, intricate system, alive with motion and change. In short, the Vera Rubin Observatory is more than a telescope. It's a revolution in how we observe, record, and understand the cosmos. From the tiniest asteroid in our solar system to the most distant galaxy clusters, Rubin will provide the data, tools, and perspective needed to reshape astronomy for decades to come. Its legacy will not just be the images it produces, but the questions it helps answer and the mysteries it reveals that we have yet to imagine. The Vera Rubin Observatory has already shown us what is possible when cutting-edge engineering meets bold scientific ambition. From its record-breaking mirrors and camera to its sweeping time-lapse survey of the night sky, Rubin is poised to redefine our understanding of the universe. Its early images and discoveries, millions of stars and galaxies, thousands of new asteroids, and even pulsating stars in the Milky Way's halo, are only the beginning. Over the next decade, Rubin will continue to reveal the dynamic nature of the cosmos, capturing fleeting events in real time, tracking the motions of countless celestial objects, and building the most comprehensive map of the universe ever created. This observatory doesn't just observe, it tells the story of the universe, showing us how galaxies collide, stars are born and die, and even how our solar system fits into the larger galactic tapestry. And while astronomers will mine Rubin's 500 petabyte dataset for discoveries, The public will also have the chance to explore these incredible images, bringing the wonders of the cosmos closer than ever before. The Vera Rubin Observatory is more than a telescope. It's a time machine, a cosmic storyteller, and a revolution in how we see the universe. As the survey unfolds, we can expect surprises, discoveries, and insights that will expand not just our knowledge, but our imagination. So, as we look to the future, one thing is clear: the story of the universe has just begun to unfold, and Rubin is giving us a front-row seat. If you found this journey through hidden science, cosmic secrets, and potential alien infrastructure as mind-blowing as we did, make sure to subscribe and hit the notification bell. Don't miss future explorations into the universe's deepest mysteries, because some secrets are just waiting to be uncovered.